For our next application of the integral, I want to take a look at calculating the length of a curve, or arc length. Now, the situation here is I've got a function, y equals f of x, on some interval from a to b. Now, up to this point, we've done things like calculate the area underneath it. We've said take that area and rotate it somewhere, calculating volume. But now I actually want to look at the curve itself, this function, and say how long is it? If you think of this as a piece of string that's kind of lying there um, drooped on the floor, and you said, what if I were to take that string and straighten it out? Don't stretch it, but straighten it out. How long would it be? Right? That's the notion of arc length. And the way I'm going to calculate this is I'm going to get a different color here. I'm going to do what any good Calc 2 student would do. I'm going to cut it up into a bunch of little pieces, measure each piece, and add them all up. Right? That's what integrals do. So essentially, I'm going to, down here, I'm going to say I'm cutting the interval up into a bunch of equal length pieces. But what that's doing is it's just giving me points on the curve that I'm going to use to say, okay, I'm going to just approximate this by a bunch of straight lines. Right? And sometimes the straight lines are going to be very close to the curve, and sometimes, depending on how much the curve is curving, the straight line may not be very close at all. But I can do lengths of straight lines because I've got Pythagorean theorem here. For instance, if I know that this length here is some change in x, and that this height here is some change in y, then I'm going to use s for arc length. I'm going to call this delta s over there. Then I know that delta s is, a little change in arc length, is going to be the square root of delta x squared plus delta y squared. Tell me how much the x changes, tell me how much the y changes, and I can tell you at least the straight line distance between those 2 points. Okay. Now, what I want to do is I want to do that for each one of these line segments as you go across, and then add them all up. Of course, then I'm going to want to do it for a subdivision of the interval with more subdivisions, so n would be bigger, and then I'm going to take a limit as n goes to infinity. But before I do that, let me just take a look at this thing here. I want to do a little bit of algebra. Let me factor a delta x squared out of that thing. So under the square root still, I've got a delta x squared times 1 plus delta y squared over delta x squared. And then the delta x squared can come out of the square root, and I'm going to write it on the back side. So this looks like the square root of 1 plus, and then this actually I can write as a fraction, delta y divided by delta x squared times delta x. So this came out of the square root to be that. And this thing is just, this is how we multiply fractions. You multiply the numerators together to get that, and you multiply the denominators together to be this. But now I'm looking at something here of a change in y over change in x, that as I take the limit, I want to now take the limit as delta x goes to 0, or as n goes to infinity, right? And this thing will have that this delta y divided by delta x, delta y divided by delta x is going to go to the derivative, dy dx. Okay. And so what I have is that a little bit of arc length looks like the square root of 1 plus dy dx squared times dx. Now I got a couple different ways that I think of that. This is the first way, just Pythagorean theorem. But then this dy dx, remember y was a function of x. Up here, y was this function of x. So dy dx is the derivative of that thing. And what I have is that a small change in arc length is calculated by 1 plus the derivative of the function squared times dx. And so the total arc length is going to be the integral from your starting point to your ending point of all these little bits of arc length. Okay. Now I said there's another way that I think of this. I'll do some examples here in a moment, but the other way I think of this um, is this way. Let me get my picture again. So I've got my function. Just each one of those little subintervals, let's say it starts here and it ends there. And, well, actually not even one of those subintervals. If I'm looking at this and I say, if I move over by a distance of 1, how far up does the function go? Well, at least I know how far up the tangent line goes, right? Because the tangent line here, the slope is the derivative. Slope equals f prime of x. Well, the slope means rise over run. So if I have a run of 1, the rise must be whatever the slope is. So that distance right there is 1. Distance of 1 over, distance of the slope going up. Rise over run is the slope. Now I'll look at Pythagoras on that triangle, and I get that this diagonal length here, which we'll call, for the sake of argument, let's call it ds. That ds here looks like it just disappeared. There it is. The square root of 1 squared plus the derivative squared. Now, maybe I'm a little hesitant here in that actually this isn't a 1. This ds isn't when I move over 1, but if I only move over dx. So if I scale this thing down from 1 to dx, that is, I multiply each side by dx. So this side would be dx, this would be dx, this would be, well, I still want to call that side ds. But the whole thing, scale it down from 1 down, then this whole thing just scales down to that times dx. Okay. There is a triangle that has a 1 and a slope here, so that the Pythagorean theorem would be telling you that other side. Then scale the whole picture down by a factor of dx to make it small, to see that that little bit of arc length is there. All right, let's do one example here on a calculation. How about just something like, how about a sine curve? How about y equals sine x from 0 to pi? We've used this all sorts of things. We've rotated it this way, we've rotated it that way to calculate area and volume. I want to actually calculate the length of the arc now, all the way over. So this is, why does that keep happening? This right here is y equals sine x. And I got x between 0 and pi. Okay. So the derivative, y prime, is cosine x. So my arc length formula here is going to be the integral from 0 to pi of the square root of 1 plus the derivative squared. So the derivative is cosine x. I need that squared, then times dx. Now, I don't think there's any way at this stage of what we've learned that you're going to be able to do this by hand, but that's okay. You can use your calculator. I will point out that the problems in the book, generally they're very careful about what functions they ask you to find the length of, so that when you do this, something nice is going to happen, and either the square is going to go away, or you're going to have something inside and outside where you can do a u substitution. Anyway, in general, this is a pretty tricky integral to do, and so you just use your calculator, you just use your computer algebra system, whatever you have available to you, and see what you get. My calculator thinks for a moment there, actually takes a little longer than I would expect, and it tells me that this is 3.8201977789. Well, anyway, I look at that and say, does that seem like a reasonable answer? First of all, if I just went straight across from here to there, then yeah, actually that is a really good thing, because straight across would just be pi, 3.14. Um, if I tried going on, just a diagonal up to there and back down again, that turns out to be about 3.7 something. I used Pythagorean theorem on pi over 2 and 1, right, to get that diagonal length and then double that result. That would be about 3.7 something. So 3.82 looks pretty good, a little bit longer than that 3.7. Not so much as going straight up and over and down, because that would be 1 plus pi plus 1. So that would be like 5.14 something. So that does seem like a pretty reasonable result. One of the things that I noticed is that my calculator took a while to do this calculation. I'm not sure why it took quite so long for this one. There are some other ones that in the next video I want to talk about some of the problems that your calculator is running into and ways you can get around it. Anyway, there's arc length.